integrating judges. Imagine a future where every cancer patient gets the right treatment at the right time. I'm Logenthiran Machap. Alongside with my colleagues, we present OnConnect, a network-guided classification framework that revolutionizes how we identify cancer subtypes. By integrating advanced algorithms, biological networks, OnConnect delivers faster, more accurate insights, enabling personalized treatment decision and better patient outcome. Okay, our innovation aligns with SDG goal, good health and well-being, because when it comes to fighting cancer, precision is power. So these are the content that we're going to cover in this presentation. Problematic insight. But before we can solve the problem, we have to face the reality. In cancer, gene expression data is a double-edged sword. It's full incredible potential, but it's high-dimensional and noisy. Thousands of signals mixed with noise, hiding the truth we are looking for. Worse, most traditional methods look at the numbers, but ignore the story behind them. They miss the biological context, the way genes actually interact inside the human body. And yes, deep learning can uncover complex, non-linear patterns, but too often these models are black boxes. We can see the prediction, but we can't see the reasoning. And in healthcare, trust depends on transparencies. So these are the barriers, and breaking them is exactly what OnConnect was built to do. So how do we break through the barriers? Our mission with OnConnect is simple yet ambitious: to build an intelligent network-guided framework that can see through the noise of high-dimensional gene expression data and uncover the truth hidden within. We set out this journey with three clear objectives. First, to integrate biological network information with gene expression data for selecting biologically relevant and statistically significant features. Two, to design and implement the OnConnect framework, combining deep learning-based feature extraction with multi-class SVM for robust cancer subtype classification. Three, to evaluate the OnConnect framework on cancer genomic dataset for accuracy, interpretability, and clinical relevance. And this is how our solution comes in. We call it OnConnect, an intelligent network-guided feature extraction and classification framework. It starts by weaving biological network information directly into the analysis, ensuring that every feature isn't just mathematically relevant, but part of the real biological story. Then, deep learning models work to extract the most powerful signals from vast, noisy dataset, while a robust multi-class SVM delivers precise, reliable classification of cancer subtypes. The result are methods that are accurate, interpretable, and clinically meaningful, giving researchers and clinicians predictions they can trust and ultimately bringing us closer to truly personalized cancer treatment. OnConnect's power comes from four core strengths. 1. Network-guided feature selection. We use real biological networks, so every feature has meaning. 2. Deep learning for representation. Hidden patterns become clear, actionable signals. 3. Handles high dimensionality. We cut straight into what matters most. And 4. End-to-end modular design. From input to classification, everything is seamless yet adaptable for future. 4 pillars, one mission: to make cancer subtype prediction sharper, faster, and smarter. Our work begins with two key sources, data sources: gene expression data, showing which genes are active by how much in cancer sample, and we source this from large-scale projects like TCGA, the Cancer Genome Atlas. Gene network data, on the other side, maps how genes interact and work together in pathways from curated databases such as Reactome, KEGG, NCI, HPRD, and so on. For breast cancer BRCA, these networks real distinct patterns for luminal A, luminal B, HER2 enriched and basal-like subtypes. By combining expression data with network structure, we turn isolated numbers into a connected biological story, the foundation for our framework. So here you can see a sample of a luminal A network with subtype network with the different colors, shade, and different size of the gene here. So the bigger the size of the gene, the more significant the gene is. So if it is green color, then it's strongly repressed, and if it is red color, then it's strongly expressed because it's a gene expression data set. Validation. To prove our framework works, to be validated in two ways. First, the confusion matrix. High values on the diagonal mean our BRCA type predictions are accurate and consistent. Low of diagonal value, minimal misclassification. Second, gene cards validation. We check our selected genes against this trusted database to confirm they are linked to real documented cancer biology. Together, that's statistical proof and biological proof, ensuring our results are accurate, reliable, and grounded in science. Novelties. What makes our approach different? Comes down to 5 novelties. 1. Biology-aware feature selection. We choose features in the context of a real biological network. 2. Hybrid deep and classical learning pipeline, where deep learning for complexity and classical learning for clarity and stability. 3. Latent feature embedding. We turn noisy data into a clean, meaningful representation before classification. 4. Modular and adaptable design. Every stage can evolve for new data, new diseases, and new methods. 5. Targeted subtype level prediction. Not just cancer detection, but exact subtype identification for personalized treatment. So the 5 novelties, one step closer to precision oncology. Social impact. The real impact of our work is threefold. 1. Improve patients' outcome. The exact subtype detections means targeted treatment and better recovery chances. 2. Advances cancer research. We deliver biologically validated insight that accelerate discovery. And 3. Supports precision medicine from one size fits all to care tailored to each patient's cancer. 3 impacts, 1 goal: saving lives while driving science forward. Possible collaborators. To make this real, we need the right partners. For example, hospitals for clinical data and direct patient impact, cancer research centers to validate and deepen biological insight, pharmaceutical industry to speed up targeted drug development, AI and bioinformatics startup to scale and adopt the framework. Together, we can move precision oncology from theory to practice. Our potential commercialization starts with 2 sectors. Hospitals, integrating our framework into diagnostic for faster, more accurate treatment decision. Cancer Research Institute, using it to accelerate biomarker discovery and strengthen translational research. Together, they get precision, and we create a model that delivers both clinical and research value. This is a publication that has been submitted for a conference and still under review. Thank you for your time and attention. Thank you. Together, we can bring precision oncology to those who need it most.